Hey, Bio One students, welcome back to another installment of Biology Virtually. We're going to go over Chapter 2, which is the nature of matter. We're going to kind of split it up in a couple sections, but as you can see from the title, nature of matter sounds like a chemistry topic, and it is. And you might ask yourself, why are we going over chemistry and biology? That's a good question because I know we're studying life, and this is not a chemistry class, but you have to understand there's a lot of chemistry in living things, including ourselves. So to have a firm understanding of biology, you got to have a little foundation in chemistry. So you'll hear me go over maybe some things you've already heard of before in middle school science and places like that. And just look at this slide, for example. It says, what are you made of, right? So we're made up of different compounds and elements. It's like a building's made up of brick, steel, glass. We're made up of chemical compounds. So you have to look at not just what's inside of us, but you also have to look at what do we breathe, what do we eat, what do we drink. All those things keep us alive every day. If it's not for chemical reactions and elements and compounds, you and I don't exist. So I think one of the first jobs that biologists need to understand is, what is that chemistry of life? That's a good question. And I'll give you a simple analogy. My sophomore year in college, I decided, hey, I'm going to be a biology major. So I go in, I meet with my college advisor, which would be the equivalent of a guidance counselor here at the high school. So I go in and say, hey, I'm going to be a biology major. What classes do I need to take to get graduated in 3 years? And she starts listing them off. Organic chemistry, inorganic chemistry, biochemistry. And I'm like, whoa, wait a minute. I'm like, maybe you misunderstood me. I'm not signing up for chemistry as a major. I want to be a biology major. She goes, yeah, I know these are prerequisites, which means you have to take these before you can take your biology, your chemistry, your botany, your zoology, your genetics. And then after I took those chemistry classes, then I understood, oh yeah, it makes sense, because I was able to understand how biology systems work by understanding how chemistry works. And it all starts with the atom. So if you look at an atom, the blanks filled in for you already, but that's the basic unit of matter. What is matter? You guys know, and we're taught in junior high that it's anything that occupies space, which could be a gas, could be a solid, could be a liquid. It's everything. And all these things are made up of atoms. Now, the concept of an atom comes from a Greek philosopher, actually, Democritus, which was 2,500 years ago. So this is not a new concept. So I just want to play a little quick video for you and understand. I'll give you a little disclaimer. This guy is a little bit crazy, but I don't want you really to get caught up in his theatrics and his craziness. I want you to listen to how far we've come with the knowledge of an atom. So who is Democritus? What did he do? What are some of these other scientists? So, and I apologize. There'll probably be a little echo with the sound. Just kind of bear with me, and we'll watch this video, and then we'll talk about it in just a second. So here we go.
History of the atom. The atom, the fundamental building block of the entire universe. But we didn't always know what the atom was or what it was made of. Although many have contributed to our understanding of the atom, 5 men stand out: Democritus, John Dalton, J.J. Thomson, Ernest Rutherford, and James Chadwick. Democritus was a Greek who theorized, amongst other Greeks, that if you cut any substance and then cut it again, 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 eventually you're not going to be able to cut it anymore. Democritus called this piece that we can't break down anymore, atomos, meaning uncuttable. Or we've anglicized it, atom. Now, Democritus and his Greek colleagues, they philosophized that all materials made of atomos, or the atom, earth, wind, fire, water, heart, the human soul. Now that seems silly now, but it was the best explanation that they could give. until the 1700s that humans were able to do anything more than that. This is when John Dalton started to set things on fire. In his controlled experiment, he showed that when he set things on fire, if he increased the amount of material he set on fire, the material would use the exact amount more of oxygen to burn in a perfect ratio, not losing any component when you set something on fire because the masses stayed the same. Made Dalton believe the atom was a sphere. Modern atomic theory has begun. Yeah. 100 years later, J.J. Thomson was working with cathode tubes. A cathode tube is a vacuum tube that has a beam of electricity traveling through it. What he found was that the beam was attracted to a positive plate and repelled by a negative plate. The electricity had to come from somewhere, but there was no room in the Dalton model. Thomson added a new particle, which he called the electron. Thomson's new model would become known as the plum pudding model. Wait, what? What's a plum pudding?
An English dessert. Would it be easier to think of it as a chocolate chip cookie?
Yeah. With the chocolate chips being the negative electrons and all the dough being the positive portions of the atom. Play that funky electron music. It's just like a cookie ride. Rutherford set out to prove the Thomson model and explain some little things that just didn't quite work. Rutherford shot alpha particles at a very thin foil of gold. What he expected to find was the alpha particles to always fly straight through the gold. What actually happened was that every 10,000th or so alpha particle flew almost straight back. What? The only logical conclusion was that atoms could not be just a positive matrix with little electrons stuck in them. All the positive stuff had to somehow be in a very small area in the middle of the atom. Not only had Rutherford proven that the proton existed, he showed that the proton existed in the nucleus or center of the atom. Protons, 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 protons.
Okay, enough of that crazy guy. But I think you guys understand a little bit about how things have evolved. Yeah, Democritus, he was right. You can only divide things so far, and then with eventually it'll get to a point where you can't divide it anymore, and that's where the atom's at. And he's kind of given credit for naming the atom. You probably caught that on the video. He called it atomos. Now we call it the atom. But that's pretty impressive that something from 2,500 years ago is still being talked about today. Now, he didn't have any understanding of what the atom was or where it was at, or electrons, protons, neutrons. That was Rutherford and all these other guys that came along later and discovered that. Now we understand the atom. We understand that we have electrons, we have protons, we have neutrons. You guys know all this. This is nothing new to anybody. They're incredibly small. I think this is a great analogy or visual picture. If you think about how small an atom is, if you take 100 million of them and put them side by side in a row, right against each other, it would take 100 million of them to make the side 1 centimeter, which is your little pinky, the width. That's it. That's crazy. So, we have really struggled with that because they're so small, and we do have quantum microscopes that kind of give us a kind of an image of an atom, but they're so tiny. And then you talk about subatomic particles that are even tinier. You can see why it took all these 2,500 years of research to come to the point where we're at now. And it's not a chocolate chip cookie. It's not that way. We know the protons and neutrons are in the nucleus, and we know the electrons circulate or orbit around those in these electron shells. So let's kind of stick that up here on the screen. Okay.